Thank you everyone to be here. It's a pleasure because it's a long time that I try to plan this course for PhD, and eventually now it's here. So with Mattia that prepare most of the slides that you will see. We were talking about physics-informed machine learning in more general way. So then we will focus in particular not only to physics-informed because there is a little mismatch in the taxonomy, but this is more wide range of possibility to embed in physics. So for planning, modeling, and control and estimation physical systems, so for any kind of physical system, commonly we will focus on robotics, on rigid body, but I mean the techniques that we will present in this course is not focused on only on rigid body. So I am Gastone Pietro Rosati Papini, and I am a professor here in the Department of Industrial Engineering. So now we will start. I will ask to Mattia to start the presentation. Thank you, Mattia, please.
Yeah, of course. Yeah, thanks, Gastone, also for the introduction. So yes, welcome everybody to the course, also the ones following online. So indeed, yeah, I'm Mattia Piccinini. I'm currently a postdoctoral researcher at the Technical University of Munich in Germany. And I'm working most of the time on these topics, so physics-informed machine learning for different types of applications, especially in robotics, but also sometimes more in general in physical systems. So yeah, we would like to keep the course, of course, interactive, so also feel free to ask questions. Maybe if we are a bit more people, so from online, we can also try to introduce each other, maybe also tomorrow. But our focus is also to foster interaction among you. And so let me start officially with the course. And let me give you some motivation examples, at least from the field of robotics or embodied AI, which is very emergent, of course, at the moment with foundation models. And as you can see in these videos, so you see humanoid robotics performing home tasks, and you see drone deliveries. Okay, there's a company that delivers packages with drones. There are also, yeah. Yeah, of course, yeah, come in, no worries. Okay. Yeah, we just started with the course. We were looking at some motivation examples. Yeah, of course. Yes. Yeah. I always forget we're not in Germany, so we should start maybe 10 minutes late. Yeah. Yeah, maybe from tomorrow we can also start 10 minutes later. So yes, these are motivation examples in embodied AI in robotics. So robots are amazing nowadays. Yeah, they can perform extraordinary tasks, humanoid robotics, drone deliveries, quadruped robotics, wheeled quadrupeds. We actually have it in our lab in Munich. It's fantastic. You can really do a lot of stuff with that. Waymo, of course, yes, self-driving cars are coming to the world. So basically, by quoting a sentence from Ken Goldberg at the last ICRA conference, he was asking the people, based on these figures and results, are we really reaching the ChatGPT moment for robotics and physical systems, right? So we all know ChatGPT is performing amazing in language. Can ChatGPT perform so well also in robotics or foundation models more in general? Well, maybe some of you may say, yes, we will get there, right? We will probably get there. But does this work already so well? Well, actually, these are also some examples of failures, of course, which you may have seen on the net, right? So it's true. We can already perform some cool stuff with embodied AI, but there are also a lot of examples of failures. Yeah, you see here humanoids. You see here our self-driving racing car spinning around because we were basically overestimating the vehicle performance too much with AI. So will AI ever solve everything in the physical world? Maybe yes, one day, but I think we're not there yet, right? So indeed, is AI ready to solve physical problems in the real world? Well, this is an open question, right? Some of you may say, yes, it's already there. Some other of you may say, no, it will take some time. But if you think, at least in some other fields, okay, physical problems is one big topic, of course, but there are also other topics which have been addressed by AI. One of them is vision, yeah? So if you think of computer vision, deep learning, and big data, I think we can say that they solved vision, right? Because if you think image classification, object detection, semantic analysis of scenes, these tasks are solved already very, very well. I think somebody is entering the room, but I will let them in. So I think we can agree that vision is already a solved problem, right? As long as we have deep learning and as long as we have big data, right? We can say something similar for language, yeah? Large language models, LLMs, in combinations with big data, internet scale data, they are solving language, right? So at least when we prompt a question to ChatGPT or whatever, or one of these models, right, which all of us currently use, I think, in our everyday research, ChatGPT, Claude, Gemini, Qwen, a lot more, they're basically solving language tasks very efficiently, right? So we can ask them, please shorten this sentence, please do prepare a report, and they do it very well, right? So language, we can say, is going to be solved very soon by these models. So, and now the natural question is, okay, we solved vision, we solved language, can we also solve physical systems or autonomous systems like robots with this type of models? Okay, so with LLMs or foundation models. And so, yes, this is indeed an open question, right? But let's consider why we're not there yet. Okay, so I'm sure it will happen one day, but probably it will take some time. And that's because language, if you think, it's a small one-dimensional world, right? So we just have strings of data, one-dimensional flows of words, and that's let's say a compact small world, yeah? In physical autonomous systems, we're not one-dimensional, right? We're in general n-dimensional. If you think a robot hand may have 22 degrees of freedom, cars have maybe more than 10 degrees of freedom, humanoids have 50, and so on. So the thing is, indeed, the physical world is way more complex than language. And in language, so with LLMs, as training data, we basically need text alone, right? In physical autonomous systems, we don't need text alone. We need much more. We need also the robot commands, right? So if I have a humanoid or some robot arms, how do I actually send the commands, which commands I send to my actuators? So I need the physical actuation commands. Plus, I need maybe some images of the task that I want to perform or the initial condition of the robot. Plus, I need some textual prompt, yeah? So if you think of, this is Pi0, maybe some of you know it, it's a famous VLA, so Vision Language Action model that performed actually quite surprisingly in robotic tasks. So, and it was developed by Physical Intelligence, by a company. So here the model is basically prompted with a textual prompt, like, please fold my t-shirt, and was given as input some images. Maybe you cannot see, but we're giving to the model some images taken from different cameras of the robot. So what is our initial state before starting with the task? And these tasks, so the images and the textual prompt were given as input to a pre-trained vision language model that was then outputting some tokens, some outputs, which are then processed by an action expert, which was computing then the controls to be sent to the robots. Okay, so basically we need images, we need text, and we need motor commands at the end, yeah, actuation commands. So it's a lot of stuff, yeah. It's way more than text that we need for LLMs with text alone, with language alone. And if you think of LLMs, they really required up to now a lot of data, basically all the data we find on the internet. So for example, Qwen 2.5, which is a recent large language model, if you want to read out, if a human had to read out all the data set used by Qwen, it would take 1.2 billion hours, okay, to read that data. It's a lot. It corresponds to probably 100,000 years as computed by Ken Goldberg. So it's a lot of time, to actually collect this data. But we find it in the internet. Okay, for language it's fine. The question is, where do we find it for physical systems? Because in the internet we don't have it. At least we don't have this scale of data. If you think also of sensors like LiDAR, GPS, IMUs, these are complex data that it's also hard to collect and hard to store because it's computationally heavy. So basically, for physical autonomous systems, we're lacking the data. This is the main problem, according to me, at the moment. YouTube, yes, it's true, has some nice videos there. It's like 35,000 hours probably of videos that are openly available. But the thing is, we have no physical commands there, right? It's video only. So we don't have the corresponding commands that the human maybe applied to his joints, to his legs, to his arms to execute those actions replayed in the videos. So this is really a limiting factor. And so to summarize, there are indeed some gaps and challenges to be addressed for physical autonomous systems with respect to embodied AI. And the first challenge, as we said, is data. Okay, we're lacking internet scale open data. We see something. Oh, yeah, please come in. Don't worry. So yes, indeed, one of the problems is data. We're lacking data. There are other problems. The real world is complex. It's unpredictable. It's something you cannot see completely in your data set, training data set. And we need to generalize. With our models, we see typically a small part of the domain, if we're lucky. And then at inference time, you need to take into account you will be seeing something else, something that was not in your training data, and you need to generalize to that. Not only you need to generalize, you need also to be safe, right, when deploying to the real world, and possibly also to be interpretable, okay, because the public wants to understand when you give autonomous driving to the market, people want to understand what's going on with our car. When we make a wrong decision, why that was the case, right? So this is indeed quite a lot of gaps to be addressed. There are some possible ways that we can fill the gaps, even though these are really open questions. So I would like also to ask you what would be, according to you, a way or some possible way to address these gaps. Do you have any idea? So like the lack of data, complexity of the real world, generalization, safety, what kind of things can we try to do with our embodied AI or machine learning methods in general? Do you have any ideas? Also from online, of course. These are open questions, of course. I'm not expecting any universally valid solution, But any idea? So there are some possibilities, of course. So some people now are talking about data flywheels. What it means is that basically you deploy your autonomous systems with whatever methods. They may not be running AI, they may be running standard PID controllers, whatever, but you start deploying them in the wild, in the real world, and you just use them to collect data, right? Because data is all what we need at the end, at least if we use foundation models. And so indeed, many people are talking about data flywheels. Tesla is doing something like that. They are deploying a lot of vehicles in public roads, collecting data, and then using the data to train their big models, And they're probably on a good way to achieve that. Another possibility is human teleoperation, at least in robotics and some physical systems. So a human can control the robot at a distance and use this to collect data. Of course, this is limiting, right? So a human cannot work more than maybe 8 hours a day, 10 hours a day. So you have a limited amount of time. And also, I wouldn't like to actually do teleoperation the whole day, right?
We have startup in Japan, in
Yes.
China, that it's
Indeed.
selling the humanoids to
Yes.
To general public, and then when there is an issue,
Yes.
they teleoperate robots to
Exactly. Exactly. Yeah.
How's work.
Indeed. Yeah. As pointed out by Gastone, yeah. Teleoperation is actually happening also with many companies around the world. They're deploying the robots. Waymo is also doing something like that, right? When they have a problem with their autonomous cars in San Francisco and around the world, there is some human operator sitting somewhere that takes control of the car and solves the issue that the car may be experiencing. So this is still a possible solution, of course, yeah. And then we have simulation. So simulation, of course, is a means to collect data, fast way, yeah, of course, you may say, but you always have sim to real. So you're never sure that then your simulation is accurate enough, right? And there are people spending years, of course, doing PhDs to prepare good digital twins and simulation models. And then, okay, there are other ways, yeah. The way that we want to look at least in this course, is, let's say, the method of trying to embed some physics priors in machine learning. So in other words, we still want to build generalist models, but we don't want to forget what we learned at school, basically. So we want to still try to incorporate some domain priors, domain expertise that you may have for the specific domain. So do not throw that away. Try to incorporate it in your machine learning methods. And of course, here it's a trade-off, right? So if I embed everything in my model, if I tell my model, okay, look, this is the physics, you don't need to learn anything, that's fine. But then we're not general enough, right? Then we're overfitting to that task. We just give the model a lot of information, and then the model is not able to learn, maybe, right? It has too much physical information. On the other hand, when we have no information at all, and we are on the black box side, then we're doing everything data-based, of course, yeah, no physics-based information. So in this course, we want to look at the approaches that somehow are in between these approaches. Yeah, okay, I have the pointer. In between these approaches, so everything that is somehow providing a hybrid between the two worlds. Yeah, so questions here. You will see this slide quite a lot when we have questions in the course. Any questions or comments or things you want to address here?
I'd say maybe if you think about a physical completely physical model or
Yes.
a completely black box, you can give an estimation of the number of parameters. So maybe the person, the other in the room, the other student in the room can understand what you're talking about. Maybe if you want.
The number of parameters.
Yeah.
Yeah. Indeed. Yeah, so indeed, when we're talking about purely physical models, basically, if you have a rigid body system, right? So you have a multi-body system, for example, of your robot. This may have an order of hundreds, at most thousands of parameters. Yeah, they are very, very complex models. But most of the times, yeah, please, welcome. Yeah, of course. But most of the times, when we are talking about physical models, we are on order of magnitude of tens or hundreds of parameters. And we need to identify these parameters. Yeah, this is a challenge, of course. Yeah. On the other hand, when we have black box models, depends, right? So if we have a really big foundation models, these have billions of parameters, right? 5-7 billions of parameters, even more. When we have instead deep learning models, these can still have several thousands of learnable parameters. So they are really two completely different worlds. People in the community often tackle only one of the two aspects. So, right, so either they specialize on physics-based models, they study mechanical engineering, they study electrical engineering, whatever, or they specialize in the machine learning models, right? So they study artificial intelligence, and then they don't know anything about physical laws, right? So this is a gap that somehow we need to address, at least if we want to really deploy these systems in the short term. Okay. So yes, we can maybe start with some information on the code, on the course, the structure of the course. So yes, here maybe Gastone can present it
just
this
want
part.
to give a short context about the course, why this course is here. So the course is part of Now for Mass project, that is a project where I'm the principal investigator. The project is founded by the Italian Ministry of the University and Research, MUR, under the Science Italians Fund of the 2023 for 1 million of euro. The main aim of the project is to try to do what we are looking now, so to embed the physical knowledge inside the network. Okay, and one we called this approach. Now we will get a more precise taxonomy on that, but the idea at the beginning when I wrote the project was to design these model structured neural networks. Model structure because was taking information and knowledge from the physical world, and try to embed this physical prior. The outcome of the project were the design of Model I, that is a tool on top of a general purpose deep learning frameworks to try to help you to design those kind of networks. And the idea is because if you are familiar with a physical world, sometimes you struggle a bit writing PyTorch or a TensorFlow code. And this software, I mean, the objective of the software was try to help this kind of person, the scientist, to write machine learning code that embed in physics. And the other part of the other outcome, main outcome of the project was to design a wiki page, a wiki website that was collecting the knowledge of model-based neural networks around the world. And this is an ongoing part of the project, so we are not ready yet, but we are working on that. And the idea to sell the project to the commission, I decided to focus on specific system, in particular autonomous system, where I thought that was more interesting to apply this technique, but I repeat that this is not you can apply these techniques also to a different systems. So for the project, I focus on drones, quadrupeds, and vehicles. Here, there are some PhDs that are on my research group that are working on these platforms. So then if you want to open a discussion, a question about those system with them, I am really happy to help you if you want to get more information on that. And finally, okay, so this course try to encompass the skills we learned so far and what we develop inside the project, but not only. So also because the idea of the website, the idea of the project was try to collect the general information. So this course, I hope that will help you to understand this interesting world. And obviously, I thank Mattia for the hard work because most of all the presentation here are made by him, and I really thanks Mattia for this. If you want more information about the project, you can scan the QR code. Of course, we can ask. And yeah, okay, thank you. So Mattia, if you want to continue.
Yes,
subject.
thank you. Yeah, thank you, Gastone. Yes, by the way, yeah, we will get there, but all the slides we're showing, we will upload them. They are actually already uploaded for today in the Google Drive folder that we shared with you, but I will get there in a second. So yes, let's look at some objectives for the course. So basically, in this course, we want to give you some methodological principles. Yeah. So what are the foundational principles that we can use to somehow incorporate physics priors in machine learning? What are physics priors? Where and how we can embed them in machine learning models? Different types of machine learning models. Yeah, not only neural networks. So to give you also an overview of what exists already in the literature, yeah, which is somehow quite a lot, but the field is really exploding, I can tell you. Like in these years, we see more and more work being done in this direction. What are the pros and cons of embedding physics priors? Because we have mentioned the pros, but sometimes there is also some cons. Sometimes we also want to be very general purpose and avoid overfitting to one specific condition. But so yeah, looking at the applications, what has been applied to real systems already? What are the comparisons against black box models? And then indeed discussing the trade-offs. Yeah, so being very general purpose versus being very physics oriented, bias versus variance trade-offs, and other types of trade-offs we need to take into account. We will also try to show you some hands-on experience, at least with an overview of the software tools that exist in the literature to facilitate people to actually encode, embed physics priors in machine learning. We will also be showing some coding examples, at least with the Model I framework that was mentioned by Gastone, which is indeed the software tool that we typically use when we do this type of applications. And indeed, so we would like to also show you some practical experience. We will be discussing lastly the open challenges and future directions. This I would like to make it a bit interactive, also based on your experience, maybe what are the problems you face in your concrete everyday research. So especially, yeah, we will have, of course, a bias a bit towards also embodied AI applications, at least because it's the field that I work on, and Gastone also. But we're open to discuss also other fields of interest. So yes, we have a tentative course schedule. So today it's tentative because, of course, it depends how much time we take for different chapters. But today we're going to look at some taxonomy to classify different approaches that try to embed physics priors in machine learning. Taxonomy, and maybe we will start discussing some types of applications, some types of categories, especially the first one you see in green, so the physics-guided machine learning approaches. We will learn what these terms mean, yeah? Physics-guided, physics-informed, and so on, don't worry. We will get there. Then tomorrow we will probably do physics-informed and physics-encoded machine learning approaches. Day 3, we will focus on what Gastone and I have been working on for some years now, which is model-structured learning approaches. Okay, we will get to know what that means. And then day 4, yeah, software tools, focus more on the Model I framework with some application examples. And then day 5 with some, directions, future directions, challenges, and also I think ideas on maybe if you want to incorporate some of the material, some of the ideas presented in the course, or try to extend them to your own research. We're very happy to support you doing that. Maybe also fostering new or creating new collaborations among you, and we would also be happy to support you, of course. Yeah. Yes, so we would like to keep at least some parts of the course interactive and have some exchange. Yeah, indeed. So we have uploaded the first 3 chapters in the Google Drive repository, which you should have received by me, either by email or by the PhD school. Does any of you also online? Do you all have that folder? Otherwise, we can also put the link in the chat, yeah, Gastona. If you want, you can put the link in the chat. So if any of the participants doesn't have the link, then they find it in the chat. Indeed, so feel free to download them, also to take notes during the lessons if you want directly on the slides. We're open to that. Yes, we are also recording the lectures. So if you miss one lecture, you can still see it online afterwards. We will keep them online. So just for the people attending in person, today we're here in the seminar room. Tomorrow we will be in A210 here, so in the other building, 401. And then on Friday, we're here again. The schedule is 9 to 12, but it's just an allocated time slot. Maybe we will not be using all of that. I know you're also very busy with your research, so I don't want to make you spend too much time. But okay, we can also decide that we start maybe 10 minutes later in the morning, so at 9:10, if that works for everybody, or 9:15, yeah, okay, 9:10, 9:15. Yes, and that's of course the schedule. Indeed, and as said, we are open to create new interactions. So please feel free to ask questions whenever you have. You've seen there's also some time slots dedicated to questions, so we have the time for that. Okay, and if some of you are interested, probably the people sitting here are interested in having the final credits recognized from their PhD program. So if you're only needing the credits for attending the lessons, please remember to write your name at each lecture inside the Google Drive folder. There is an Excel sheet that is called attendance form or attendance sheet. If you go there, you can write your name, name or surname. There is one tab for each day, so just remember. I will try to remember to tell you every day to write your name there. But yeah, just please do that. If instead you also need a final exam, so if you need what in Trento are called Type A credits, then of course it is optional. Yeah, no obliged to do that. But if you need that, then you can prepare a short report in which basically we want to see how you would like to incorporate some of the presented methods and use them to your own for your own research. Okay, so some preliminary ideas are nice, are enough. Maybe indeed a 1 or 2 page report in which you present the idea, maybe a preliminary diagram, what you want to develop. Is this new to your field? Okay, so something very, very preliminary. And then you can send it to us. We will evaluate it, give you feedback, and then you have the credits approved. Okay, and this is something. Okay, please do it by the end of August. We don't want to take it too long, of course, also for you, so you have the credits at the end. Okay, you admitted it. Okay, and yeah, so please do that by the end of August if you want. And this is not something that we want you to do just to pass the exam. I mean, the idea is that later, if you're interested, we can also look deeper into that, help you actually develop new methods, apply them to your research. So we're really happy to support you here. So at the end, I mean, we're also happy to write a paper with you if you like on the implementation of the research idea to your own research. And at the end, okay, if you in any case, if you do the exam or not, you will receive an attendance certificate by the university with the number of credits. So it should be 3 credits, I think, if you do the exam. Otherwise, probably 2 credits. Not really sure, but okay, on the certificate, there would also be the number of hours. So you can then convert it into credits. Yeah. Okay, questions here. By asking another question, right? So neural networks, okay, is something that maybe most of you already know. Yeah, is there somebody of you that doesn't know how a neural network works? But we're going to see that in case in a second. But just to know, you all know, yeah. So raise the hand if you know what a neural network is. You all know, okay. Maybe some of you don't know, but don't worry. So neural networks, there is this conception, at least in the community, that they are basically that they are very generalist black box models. And this is, in some cases, it's true, in some others maybe not. Yeah, let's see. But let me start from the very beginning. Yeah. So if you don't know what a neural network is, totally fine. The basic building block of a neural network, of each neural network, let's say, is the perceptron. And the perceptron is not something strange or abstract. It's just an operator. It's just a simple operator that basically receives some inputs, x1, xn, and returns an output y. And what it does, it simply sums all the inputs it receives, okay, x1, xn, sums from 1 to k of xk, multiplied by a weight, wk. So we take a weighted sum of the inputs, and we apply a bias b, okay, very simple. And then this operation, this sum of weighted inputs plus bias, is processed by a nonlinear operator, in general, f, okay, that can be a nonlinear operator, and then this becomes simply the output. Okay, so this is called perceptron, very simple. Typically, the weights, wk, and the bias b can be learnable, okay, so this can be trained by the neural network to provide the best approximation that relates measured outputs with measured inputs x.
I mean, the architecture presented it's quite old. It's from
Yes.
the 1958.
58, yeah. So it's very old, yeah.
The algorithm that was used for train is newer.
Yes.
I don't remember exactly when it was presented the first time.
Yeah.
The idea of backpropagation.
Yes, exactly. But at least the structure itself, the perceptron.
The structure, yeah.
Of course, it's derived from biology, yeah. So there are connections with biology, with the structure of the brain, how neurons in the brain work. They are basically activated. Each neuron is activated. It's like a spiking neural network, right? There are these signals. When they go beyond a certain threshold, then the neuron becomes active. Otherwise, it's deactivated. And here it's something similar. So the function f is actually an activation function for the neuron. So the perceptron is basically a neuron, if you want. The activation function f is a nonlinear operator that can activate or deactivate a single perceptron depending on its inputs. Okay. So this is indeed the very basic component. And then from the perceptron, we can easily arrive to a multi-layer perceptron, okay? Which basically means putting together perceptrons. So each of these gray dots is itself a perceptron, and we can stack them together. Okay, so we can stack perceptrons, concatenate them, combine them, and we obtain a multi-layer perceptron. And actually, it turns out there is a theorem by Sibenko in 1989 that tells that it's actually a universal approximation theorem, something very, very powerful. And this tells that a multi-layer perceptron with only one hidden layer, so in this case we have two. If we have just one hidden layer, so one line of neurons, each of them takes the same inputs, and then can return a set of outputs, can be a single output or a set of outputs. This multi-layer perceptron with only one hidden layer can approximate any continuous function. Okay, very powerful theorem, but it was proved, yeah, mathematically. So in particular, I think it was proved in the case that this function f is a sigmoid or a tanh, a hyperbolic tangent or a sigmoid.
Of course, needs a nonlinear function. There.
Yes.
Otherwise, you can't decouple the first layer.
Exactly.
From the second.
Yes.
It's only linear operation.
So we need a nonlinear operator here. If the nonlinear operator is a sigmoid, okay, so something that goes from 0 to 1 probably, or a tanh, same thing. Then by having a lot, of course, yeah. So the theorem says if this neural network is big enough, if the multi-layer perceptron is big enough, but with only one layer, but a lot of neurons, of course, a lot.
Instead of to make it
Yeah.
deeper, make it long the other
Yes,
direction.
exactly. So if you have enough perceptrons along the hidden layer, then you can approximate any continuous function to the desired precision. Okay. Indeed, as said by Gastone, this is one approach. The other approach is to have instead multiple layers. And in this case, we talk about deep learning. So deep learning basically uses multi-layer perceptrons, but with a lot of hidden layers. And then the depth of the neural network is the number of hidden layers. But this is still an interesting result, right? And this is the theory. Okay, the theory says, yes, you can do that as long as you have enough data and as long as you have enough perceptrons. But and now I'm asking you, like, is a multi-layer perceptron really the best choice for every task, everyday task that we have in our research? Well, it depends. Yeah, maybe if you have enough data, maybe yes. Okay, if you have enough data, maybe an MLP is the best choice. But in real life, do we have the data? Maybe yes, maybe not. Depends. Sometimes we have little data, and then maybe we have little data and some physics or domain priors, let's say, more in general. We have maybe data plus domain priors. Okay. And can we use the domain priors to compensate for the data we don't have? This is the question we want to ask also throughout the course. And indeed, can we exploit these domain priors, task domain priors, in the design of our neural network? So this is indeed the question I want to pose here, and we want to try to answer this question.
If you want,
yeah,
you can show a page that I think is a game, but I think gets the flavor of using structured networks.
Yeah.
This page I can post. I can.
Yes, I have it. Yeah, I can show. Yeah, it's a nice example. You're right.
This game, well, 10 seconds. If
a
you go on
TensorFlow
this
playground.
page, that is, I try to.
It's this one, right?
Yeah, if you look to playground tensorflow.org, if you want to try to, the one that have the laptop, you want to try to connect on this page, okay?
Yes.
And the objective of this page is try to, if you want to try to this game.
So here you can basically play, right? So here it says, okay, you have some data on the right. So you have the orange data and the blue data. This is the output, but you can think of a classification task, right?
Classification.
So these are the points you want to classify. The orange ones are of class A. The points in blue are of class B. So this is classification. You can also choose regression, but let's keep classification.
No,
and here you can, yeah, and this is indeed a multi-layer perceptron, right? So you can, so you can have more layers here, like 6 neurons, 7 neurons. And you see, if you change the number of neurons, the output, which should be the shaded area, right?
To click play, no, on the top left.
Ah, sorry, yes.
And now it's training and is classifying the two classes. The first layer, what does the first layer? The first layer try to create some plane, okay, here. So you can see there is a plane, here there is another plane here, another plane here.
Yes.
Okay, you have 6 neuron, means 6 plane there. And then you have another 2 layer here, 2 neurons here. And this is try to select this portion of the space into different classes. So the first one you see here, you have this orange part and the blue part. And those again, the orange part and the blue part. And then you mix up together and you classify it.
Yes. So in this case, we are able to classify quite well the blue dots. They are classified in a blue region, so the class is correct, I think. And the orange dots as well, yeah.
And it's funny if you, for example, if you choose a different data set, okay?
For example, if we choose the spiral data.
Okay, so this is interesting. Also, the one that have the laptop, if you want, we can give you 5 minutes to try to fit
I will post it in the chat, yeah.
And eventually you will find a good solution to fit the data, okay? Also for the one that are online, if you want to share the link.
Yeah.
So the objective is try to fit the spiral, changing here the parameters of the network. So you can changing the number of neuron, you can changing the number of layers. And we give you 3 minutes to try to fit the data.
Yes, so basically if you write, I don't know why Teams is so time thread. Now I wanted to post the message.
The message, I try.
But if you write basically TensorFlow Playground, you find it. If you write TensorFlow Playground is the first result that you get.
Non ti va la chat.
The chat doesn't work. Yeah, thanks Microsoft Teams. Okay. But
è sparita. Io non ci
okay, yeah, on Mac OS it's particularly funny. But yeah, if you go, I will share again the screen.
What we can do? I haven't.
But otherwise,
have an
yeah, we
idea,
can show that directly. But it's funny because you can start playing. Yeah, you can start adding neurons, see what happens. You need to click on play every time to actually train the model. And you see the results are not so satisfactory, right? At least with this type of data,
Yeah.
with the spiral data.
You tried to fit the data, changing the neuron.
So here we're training. Yeah, the loss function is going down, but it struggles. Yeah, so here you see loss function, right? This loss is telling us how good we're actually fitting the data. But yeah, okay, it tries, maybe it finds a solution, but it really needs a lot of epochs, yeah?
Try to increase the number of layers also. No, the hidden here, no, on the...
Yeah, you can also add hidden layers, yeah, indeed.
Layers.
From here you can have more hidden layers. We can try to play again. Maybe it finds a better solution, but you see here we have a plateau in the loss function, so it's being stuck in a local minimum. It cannot improve so much. And this is a quite big model, okay? This model maybe has some thousands of learnable parameters, but it's really struggling a lot, yeah, you see? It's really struggling a lot to get a good result for this.
Yeah.
But magically, if you try, okay, if you try here, okay, so the inputs here are x1, x2, okay, and this is a spiral shape, output that we want.
Yeah.
So we can actually add x squared, x1 squared as another input, x2 squared, or the product of x1, x2. Or we can also add the sine of x1, x2, okay? Yeah. And intuitively, a spiral is related to trigonometric functions, right? So you can describe a spiral by trigonometry somehow. So let's try to see if we can, using some...
Yeah, you can reduce a lot.
Maybe we can also remove that. We can use only one hidden layer, but with sine of the inputs. And you see, already after some epochs, the results look quite well, right? Or at least better than before. Yeah. So this means that if you use the right features, in this case, sine of x1 and sine of x2 are features, taking as so combining x1 x2 with some logic. So in this case, this is a form of domain prior, if you want, right? Yeah. So in this case, we know the function we want to approximate is composed of trigonometric function, okay? So a spiral can be described in parametric form using trigonometric functions. And so if we use this idea to process the inputs, we obtain a way better results with not so many epochs. We can also reduce the model complexity. Okay, did you get the idea? Yeah,
was a game, yeah. But you already get the flavor of embedding knowledge, no? Because embedding this knowledge, we reduce the number of training data, you get a better fitting, we can reduce the number of the parameter of the network, and if you reduce the number, you can also reduce the data. So this is a very simple and stupid game, but I think you get
yes,
a flavor of what.
yes,
what,
you can play around. Actually, it's
yeah.
it's quite a nice tool, and also you cannot break it, as they write here. So it's a safe sandbox in which you can play. And you can do a lot of stuff. Yeah, also classification tasks and whatever. Okay, let me share again. So indeed, this gives the flavor, right? So this gives the idea that if we have some domain priors, in this case, the domain priors were the trigonometric functions, we can exploit them to improve our neural network, at least when we have a limited amount of data and we still want to be accurate enough. Okay. Okay, so indeed, this is the question again. So do domain priors really matter in the neural network design? I think we tried to answer that already with the TensorFlow playground, but let me be a bit more general. Let me take maybe a step back and let's think what happens in specific domains, okay? Computer vision. Computer vision, some of you may know, in computer vision, one popular class of neural networks is convolutional neural networks, CNNs. These are used to detect objects in a scene, but to detect if we have a car, a pedestrian in a scene, whatever. And you may think these are very general networks, but actually it's not like that. Yeah, it's not, they're not super general networks. They were actually conceived to have, so their internal architecture was conceived to encode some ideas, some domain ideas. In this case, the domain idea was the spatial translational invariance. So it means that if you have a car in the scene, or if you have a person in the scene, the network is able to detect it for whatever position that object has in the scene. So if I have a person in the bottom left corner of the image or in the top right corner, the CNN, because of the way it's conceived, can still detect it quite effectively. Okay, and it is what we call spatial translational invariance. So you can translate the object, you still get the same results. So this is a form of domain prior, right? In an image, we want to have that. Okay, and in speech recognition or natural language processing, here we have different types of architectures. For example, long short-term memory networks, LSTMs, also a very popular class. You may think these are general, but again, they are not super general. So there, the idea is that the network needs to be able to capture long-term dependencies, for example, in language. Okay, so when we speak, maybe we make a very long sentence and the sentence is still connected, right? So maybe the sentence covers 5 lines if it's a text, but you have some long-term relation within the sentence, right? So maybe the beginning of the sentence is still related with the end. And a traditional network may struggle. So long short-term memory networks are conceived to actually learn long-term patterns and dependencies in sequential data. And they have specific gating mechanisms to do that. LSTMs are one type, but again, in the field of natural language process, transformers, very popular. So ChatGPT is based on transformers. All the LLMs are based on transformers. Many of the LLMs are based on transformers. And they are also not super general. They encode an idea, which is the idea of attention over structured tokens. So they can attend, the technical term is that they can attend, so they can learn to focus on specific regions of the input tokens. And so these architectures indeed are not super general. They encode some form of domain priors. And what about physical systems? Okay, in physical systems, domain priors are physics priors, right? And then my next question is, of course, what are domain priors? This depends on the field, but we can try to be a bit more general and say what physics priors can be. So I think most of you are familiar with the equations of motion. If we have a physical system that moves, so we can describe the equations of motion by Newton-Euler, Lagrange, Hamiltonian, whatever approaches. These are a form of physics priors. Okay, so if we have the equations, why throwing them away? Again, we can have also conservation laws that we want to embed as physics priors. For example, we don't want our neural network to lose energy over time as we integrate the dynamics, or we don't want to lose momentum. Okay, this is all something that we can incorporate. Symmetries. Okay, if our car is symmetric when we rotate, when we turn left or right, this is an important thing that we want to maybe encode in our neural network. Invariances, if we have a translation invariance, rotation invariance, again, physics priors. Constraints, if our system is holonomic, non-holonomic, we can encode that somehow. Connection structures, maybe our robotic arm is composed of two links with a revolve joint, we can try to encode that, and so on. Okay, so these are physics priors, if you agree on that. And then the next question is how to encode them, how to embed them in machine learning, how to embed the physics priors in machine learning models. Well, let's start again from something general. So I think we may agree that a machine learning model, whatever, a neural network, Gaussian process regression, foundation models, ChatGPT, whatever, they have this type of structure. So they have some input data, okay, in green. They have some training data sets in green. They have some internal architecture in orange, okay, whatever. It can be a multi-layer perceptron, it can be diffusion, it can be whatever. And then we have a loss function to train basically the model. Okay, so 3 ingredients. Do you all agree? Okay, we have we can say that this is quite general. And now my question is, where can physics priors enter? Do you have any ideas on that? Loss function, yeah, good point. Good point indeed. Yeah, loss function is one of the things we're going to look into. It's probably the most popular. Yeah.
Saying the input data set and the architecture.
Yeah, you're right. You're right. Yeah, indeed. Yeah, you're right. So in principle, as suggested, you can inject it everywhere. So if you are, I mean, in principle, there's nothing that prevents us from injecting physics priors, whatever, inputs, data set, architecture, loss function. And this is exactly what we're going to see in the course. Okay. And we have different terms to name each of the approaches. Let's start from inputs, okay, as suggested by Davide. So we have, in this case, we call them physics, we call this approach physics-guided machine learning, okay? Physics-guided machine learning is when we try to incorporate domain priors or physics priors inside the inputs or data sets of our model. Okay, so what this means is we have some raw sensory data here, for example. We can have our camera, we can have our LiDAR, whatever. We can have some ways to process this data, to pre-process this data, and extract from this data some useful information. And useful information can be, so for example, consider the IMU data on your quadruped robot here. This can have IMUs mounted, so inertial measurement units, recording the accelerations. What if we can convert these accelerations to center of mass forces, right, as depicted here? Or same for our car. Okay, we have IMUs, we have speed sensors, wheel speed sensors. Can we convert these measurements into center of mass forces? This is something we can do. And we can do also with traditional Kalman filters, with traditional estimators, whatever. And then the idea is, okay, we have something here to pre-process the inputs. This something can be pre-trained. It can also be a neural network. If it's a neural network that, for example, processes camera images of our car and transforms the camera images into some physical quantity, accelerations, velocity, whatever, then this type of neural networks should be pre-trained. So we don't want to train them together with our main architecture, okay? Because still we're talking about inputs, okay? So acting on the inputs of our machine learning model. So this is the first class, physics-guided machine learning. We call it like that. But there is actually a second class, which is physics-encoded machine learning. And here we talk about physics priors in the architecture. So this means this is a huge set of approaches. We will be talking about that tomorrow and the day after. But here the idea is, okay, let's open the black box of a neural network, of a machine learning model, and let's try to have some, for example, physics layers, right? So instead of having a perceptron, in one of these layers, we can have a physical model that tells that the forces are given by the mass times the acceleration, just as a very generic example, okay? We can also structure the connections. So instead of taking sums of the inputs, we can take something else, products, if it makes more sense, or whatever. So this is another huge class of approaches. We call them physics-encoded learning. And then the last class, yeah, which your colleague was mentioning, is the one in which we act on the loss function. And this is the most popular. This is called physics-informed machine learning. By the way, this gives the name of the course as well. Yeah, this course is called physics-informed machine learning. But this is because, as we will see in a second, there is confusion in the community. So a lot of people talk about physics-informed machine learning. But it's, yeah, but they are doing maybe physics-encoded or physics-guided, yeah? So there is a bit of confusion. We want to make some order here to clarify things. So physics-informed rigidly means incorporating physics priors in the loss function. The loss function is the one you use to train your model. Okay, so it's something that tells you, please minimize the deviations of my model outputs y with respect to my ground truth measurements y hat, for example, if you have it. So this is L data. It's the one you typically have in 99% of the machine learning approaches. What physics-informed neural networks do, or physics-informed machine learning, is they add another term to the loss function, which is this L physics. And here it's where we can inject, for example, we can force the model to satisfy some equations of motions, some ordinary differential equations, and so on. Or we can force the model to satisfy some boundary conditions or some physics relations. So we can inject other forms of loss functions. Typically, we have always quadratic loss functions because it works better for optimization. Yeah, we have a convex cost function, it's better. But this is the general idea, okay? I just want here to give you the very general idea, okay? So again, physics-guided inputs and data set, physics-encoded architecture, physics-informed loss function.
I want to mention also that now we focus on those three because are the most important, but there are another place where you can embed the physics. I just want to mention.
Yes.
That is the possibility is the training, so the phase of training. So you can also embed the ideas or something that comes from the physics world when you train the network. For example, just a simple idea. For example, you have a complex model, and you say, okay, maybe some part of this model I take the parameter fixed. I train part of this model because I know that they are the main parameters I want to fit. First of all, those parameters, and then I block these parameters and they train the other part of the network. So also the training can embed some ideas that come from physics. The other place where you can put physics priors are the validation, the final validation of your network. So sometimes you can say that your network is based only on this validation. Okay, so based on those functions, but the idea that you can validate your network with a different approaches that maybe is more similar to a physics world. So for example, in some of our work, we did a spectral analysis of the network. That is something that you do when you make a physical model. And the just an small adjustment, what I said, related to physics guided. We here in this section we compress input and data set, but of course are two different words. No? So in one case, you can pre-process the data set to create a new data set and then use this new data set to train the network. In the other case, you can insert a piece of the network that pre-process the data during the training. Okay, so are small differences, but yeah. So in common, finally, you can have 6 levels. Okay, so guided in input or dataset, architecture, loss, train, and validation. Just yeah.
Yes, indeed. So these are the most popular 3 categories, but Gaston is right. So one can also perform the training in multiple steps to encode the physical principles, whatever. Yeah, we will see some examples probably in the next lectures. Okay, so if this is clear, again, yeah, this is taxonomy, what we said. So in the community, there is confusion. Many people talk about physics-informed machine learning to mean everything. This is fine, but then we don't understand really what's the difference. What we do is we follow the taxonomy. So we're not introducing the taxonomy. We're following a very highly cited survey paper 2024 by Farughi et al. That introduced exactly this taxonomy. So physics guided, informed, encoded neural networks. Their survey is specific on fluid and solid and solid mechanics, but it doesn't matter. Okay, the taxonomy remains that, and we will follow that throughout the course. Okay, questions? Yes.
And how do you call if you have part of the model like a network?
Yeah. You have part of the model.
We have a vehicle model.
Yes.
And you have some part of
some neural terms.
Yeah.
This would be classified as a physics encoded architectures. Okay.
Yeah.
So in this case, you're acting. You can think of okay. So Giacomo made the example of a vehicle dynamic model. So you can have physics. You can start from a physics-based model. This is something we do in our research, and we inject some neural terms here and there where we know the model is not so accurate. Okay, so in this case, you can see the whole model as a big neural network, even if it consists of physics-based equations plus neural terms, but you're acting on the architecture of the model, right? So you're manipulating the architecture and creating neural connections mixed with the physics connections.
Probably also you are doing implicitly, you are changing the training procedure to maybe you fix part of your physical model and then you may train this specific, you change the data set and then you train a specific part of the network. So
yes,
you are doing encode plus train physics.
Yes, indeed. So one can indeed have a mixed physics neural model and then train it in multiple steps. Maybe you freeze the physical part and you unlock, you want to train only the neural network terms. But this is indeed a nice example. We will see a lot of examples in the next lectures.
Yeah, the last thing that you can compose. I mean, you are not,
yes,
you can use guided with encoded, with informed. I mean,
yes,
are not also Mattia showing in the picture that you can create a network that use all the approaches together. So
yes. Indeed, yeah. In principle, you can combine the approaches. They are not so. It doesn't mean that if you do physics informed, that you can also do physics encoded. I mean, in principle, you can combine everything together. This is what actually we would like to bring as a message, to you, to the community in general, that 99% of the approaches are doing only one thing.
Yeah.
They are either using physics guided or physics encoded or physics informed. But the real potential comes from combining them, probably. Of course, it's an open discussion here, but yes, in principle, this is feasible. Okay. So this closes the introduction. Today, maybe we can start looking at physics-guided approaches, the ones in green, because it's the smallest category. So I know today maybe you're a bit tired already, but this is a small part. We can do that easily today. Maybe we can take another break. 10-minute break. Then we look at physics-guided, and then we close it for today, and we restart tomorrow. Okay. So yeah, 10-minute break, and then we continue. Okay, good. So last part for today, we're going to introduce one of the 3 classes that we mentioned before, which is physics-guided inputs, data, and representations. So this is indeed one of the 3 big classes that we mentioned before. And again, some positioning. So I think now it's clear we're talking about this part. So the first of the 3 big blocks. And again, so what does physics-guided learning include? Well, we refer again to this survey paper, which we mentioned before. The first part is about physics-guided representations. But actually we give here, we adapt the classification to what we show here in the course. So what we mean, what this category includes is approaches that somehow embed the physics insights into the input features of our model, into the data representations, so training data set representations, but also training data selection and generation with physics-based insights. Okay, we're going to see what that means. Yeah, we have in general multiple classes here of approaches. Here we classify 4 main classes. Yeah, the first class is the one in which we somehow have physics models as inputs for neural networks or machine learning models. So what this means is we have a set of raw measurements, typically, okay, sensory measurements, whatever. We process the measurements with some physics-based model, if you want. Can be any type, can be a Kalman filter, can be an estimator, can be whatever, physics laws that you may inject, can be a dynamical system. And then we give the inputs, the physics-based estimates or features, we give them to our more generic neural network, okay? And then we have our outputs. So very general class.
In this case, the Kalman filter or this pre-processing speaks during the...
Yes, exactly. So the Kalman filter, or can be also, something else, model-based, physics model-based, but it's something we tune before actually using it inside our neural network framework. So we keep it frozen, we don't train it, but we use it to pre-process the inputs, the raw sensory inputs. Okay, second category is still partly related to that, but it's more about physics-guided features and training data. So here it means we can have, again, a raw sensory measurements, but from the measurements or from a set of features that we have pre-computed, we extract another set, or we create a new subset of features with physical principles. Okay, so for example, if we measure the velocity, we may create new features based on the velocity. For example, it's the sign of the velocity, or the squared of the velocity, because, for example, we know the squared of the velocity is related to the aerodynamic drag or whatever. Okay, so based on a set of features, we create new features embedding physical ideas, or we create new features. And then again, we give the new features to our neural network as inputs. Okay, then there is another subcategory here, which is training data, right? Here we said physics-guided features and training data. So here we want to actually make sure that our training data set, for example, is physically consistent. So we want to generate data. If we generate data using a simulator or using another machine learning model, we want the data to be physically consistent. So maybe we post-process them to ensure physical consistency, or we generate them with physics-based simulators, validated simulators. So all these type of ideas can be collected inside this second category. Okay. And okay, these are the first two. Then we can have in general another category, which is a bit more theoretical and which is called geometric learning. So here it means we have still our set of inputs, but somehow we project them or we process them in such a way to make sure they satisfy some geometric properties. For example, if we know our system has some symmetries, yeah, left-right symmetries, for example, our car, okay, we can make sure that the data we have recorded satisfy these symmetries. If they don't, we force them to satisfy the symmetries. Or we can have, yeah, indeed, some other geometric structures that we want to preserve. Yeah, for example, in robotics, SO3, SE3 spaces. Okay, these are theoretical constructs. I don't want to go into the details. But there is actually a bunch of possibilities we can use to encode geometric structures into our data representations. Okay, so basically, this is still operations we do on the inputs. We can project them on a certain subspace, yeah, like in the case of SE3 representations of robotics, and manipulate them, and then we give the inputs to the neural network. Okay, that processes them further. But this is geometric learning. It's also related to geometric reinforcement learning, but again, it's something very technical. I don't want to get into there. And then the last category is frequency domain learning. Yeah, this is something Gastone was mentioning also before. So basically, instead of taking our data in the time domain, we can pre-transform them into frequency domain with spectral analysis, with the Fourier transforms and so on. And then the network operates in the frequency domain. Yeah, this can be done. For example, with physical systems, we don't want to learn the high frequency components, which are typically noise. Okay, so most physical systems have a limited bandwidth, maybe of 10, 15 hertz. We want our system to learn those frequency, avoid overfitting noise. And so we can pre-process our inputs in the frequency domain, extract, for example, the low frequency content that we want to use, and then give that data to the machine learning model. Okay, so very generally speaking, this is another category of approaches that still act on the inputs. Okay, so this is an overview, yeah, of the 4 categories. And just as a remark, when we talk about physics-guided input data representations, as we said, we can also have actually neural networks here. So this one can be actually a neural network, but it needs to be, as we said before, pre-trained. So pre-trained before training the main architecture, or be non-trainable. Okay, so if it's a Kalman filter, it's non-trainable, that's fine. If it's a neural network, we pre-train it, we freeze it, and we use it as is.
Yeah, okay. This is the motivation is because otherwise you can decouple the architecture from the physics guided, because if you have a network that is trained in the main training with their main architecture, I mean, is the architecture of the network. Okay. So to be sure that you are doing physics guided, I mean, it's just a matter of names.
Yeah.
It's not a problem. But yeah, to distinguish, if you could retrain the network and then you use freezing the weights in the main training, this is physics guided.
Yes.
Otherwise, is an encoding.
Yes, exactly. So if you unlock the neural network term here, if you have any neural network here and you unlock it, then it may be interpreted, it depends on the architecture, yeah? But if you unlock it, then it may be interpreted as a physics encoded architectural model.
Is very...
Yes.
Become very...
Yeah, it's very subtle. Yeah, it's not so clear, but at least when we do this type of operations with pre-trained or non-trainable models, we classify them as physics-guided approaches. Okay. And then let me start with the first category here. We're going to see actually only the first two categories in more detail. So first category is physics models as inputs for neural networks or machine learning models. Okay. So yeah, very intuitive. Yeah. So here we want to use our sensory data. Can be, yeah, cameras, IMUs, whatever. We pre-process them with a physics-based model, and we send the output to our neural network. So basically, we want to, to generate input features that are physically consistent. So we want to ensure our machine learning model learns in a physically consistent space and not in a more unstructured space. And from here, okay, we can see some examples. Okay, some examples of real papers. This is, for example, a real paper from 2019 in which the authors wanted to make a side slip estimation for a vehicle. Okay, this is something maybe most of you don't know what it is, but the side slip is basically the angle beta between the longitudinal vehicle velocity Vx and the lateral velocity Vy. Okay. So every time we drive with a car, our velocity is never aligned with our longitudinal axis unless we're really driving straight. But when we are in a corner, our total velocity vector is not aligned with our longitudinal direction, and the angle in between is the side slip. This is something very tricky to measure. It requires GPS, very complex systems. So they wanted to estimate that, yeah. And their idea was, okay, let's use a neural network to do that, but let's have a physics-guided neural network design. So they had actually their main neural network architecture was this one. It's called GRU. It's a gated recurrent unit. It's a recurrent neural network, yeah. So basically, it's like a dynamical system, but written as a neural network that processes a set of measurements.
Structure with respect to LSTM.
Yes, it's similar, exactly.
The same,
yes, it's similar to the ones we mentioned at the beginning for language processing, so LSTMs. But okay, it doesn't matter. It's a neural network. Okay, it's called GRU, very general purpose. Here, their idea was to use a physical model to compute a physical quantity, which is the derivative of the side slip angle, beta dot. So they wanted to estimate at the end beta, okay, the angle. But they used a physical model to estimate beta dot, okay, the time derivative of beta, and then fed this quantity to the GRU together with their other inputs, x. And this actually turned out to outperform the neural network without the beta dot estimation, and also a traditional physics-based model. So basically here, what they did is they used still the raw sensory data of the car. So the lateral acceleration, the velocity, the yaw rate. They use these signals to pre-compute beta dot with a very simple relation, actually, analytical relation, physics-based. And this helped tremendously then the neural network results, the accuracy. And this is just an example, okay? The idea is, again, use a physics-based model, compute a physical quantity, give it as input together with the others, the neural network. And indeed, so you can apply this approach to many other fields, I think, yeah. Second approach is the one in which we want to have some physics-guided features and training data, which is still related to the previous one, but here we act more on the features and the training data themselves. So again, the idea here is we have our measurements. We can have some pre-computed features like velocity, accelerations, whatever. We add some new features. So maybe we compute energies from velocities, we compute forces, whatever. And then we have our full set of features, of signals that we give as input to our model. And here it's where we embed our physics knowledge. So in computing new features or selecting only the one we want. And the second category is the one which we generate physically consistent training data. So what we said before, using physics-based simulators or post-processing the generated data. And this is an example of the first case. Okay, so input features. This is an example in the field of feed-forward control of linear motors. So they had this linear motor, and they wanted to compute, they wanted their neural network to compute the control input. So in this case, the force, the linear force, to track a desired position of their final actuator, final position Y. So they had this model, and they had, you see, as output, we have actually the input. Yeah, so it's actually a controller. It's not a dynamical model. So the output is actually the control force U hat, and the input is a past history of controls and a past and future reference for the output Y, which is the position. Okay, so they have a planner probably that computes their future desired position. They give it as input to the model, and then the model returns the force to be applied at the current time step. And this is the baseline model. But then they say, okay, let's use some physics-guided insights here. Let me admit, okay. Let's use some physics-guided insights. In particular, they use the fact that linear friction in their case was depending not only on the position, but also on the velocity, so the derivative of Y and its sign. And these are additional features, okay, additional inputs that you can use by simply pre-processing the ones you already have, the position, and giving them as input to the neural network. So in their case, they added this set of features, new features, velocity, sign of the velocity, to the neural network. So this then go among the inputs that you see here. They extended this vector of inputs. And it turned out this was outperforming the baseline model without this set of features. So again, this is something more general that you may think also in totally different fields. But the idea is very simple, yeah, nothing really special. But it helps. It can help speeding up the training. And this is, by the way, what we were doing before with the TensorFlow Playground, yeah, which I posted now in the chat. I'm not sure the ones online could see that, and don't remember if I shared the screen while we were doing that, but probably yes. But in any case, from TensorFlow Playground, we were showing that by adding features, in that case, the sign of the input features, we were obtaining way better results on a spiral problem, classification problem. So even in that case, it would be a domain-guided approach. Okay. And last example, or yeah, another example is here from another paper, 2025. This goes in the direction of foundation models, actually. So here they wanted to generate human motions with some characters. Okay, the blue characters you see are from a simulation environment from Isaac Jim, which is an open source simulation environment. And they wanted to generate human motions in parkour scenarios. Yeah, so the human had to climb some steps, go down, go up, go down in a simulation setting in Isaac Jim. And so what they basically had is a diffusion model, here a motion generator that was generating the motion for their character. Okay, and this one was a diffusion model. Diffusion models are a type of generative AI models like transformers. So, for example, the models that generate videos now, the video generation models that you see are emerging now, or also the ones that generate figures. Yeah? When you ask ChatGPT to generate an image, it's using a diffusion model to do that. So here they are using a diffusion model to generate the human motions. But a diffusion model is something very general purpose, yeah. So it can generate images, it can generate trajectories, And then who knows if the trajectories are physically plausible or not? Yeah, probably not. And indeed, what they're doing here is they are generating the motion, okay, with a diffusion-based model, but then they are using a motion tracker, a policy pi. This is simply a physics-based tracking controller. You can think of PID controllers, MPC, whatever type of physics-based controller to track the human motions, the generated human motions, and obtain as output physically consistent motion. Okay, so they were post-processing this motion with some tracking controllers to make it feasible. And then what they were doing is they were reusing the corrected motions to refine their diffusion model, their motion generator. So they were recycling the outputs of the motion tracker, so the physically plausible motions. They were recycled, put them in a data set, D, and use the data set to refine, to retrain their diffusion model. And in this way, they could improve the results, yeah? So with respect to the baseline diffusion model alone. So this is another example in which you can indeed act on the data set, in this case, on the training data set, by post-processing your maybe non-physically consistent data, make them physically consistent, and then plug them in your data set. Okay, and yeah, questions here on the chapter. Curiosities, yeah, indeed, discussions, whatever. Or if you have some thoughts, like this is something that could be applied to your research somehow, or of course, this is something general, right? We're not, so this chapter is probably the most general one, yeah? So we're not really doing anything really special to encode physics. We're just using some tricks to improve our models.
Yeah, sometimes it's very stupid, but it's effective. I mean,
Yes, exactly. I mean, they can seem very simple tricks, but if you go and look at these papers, they show actually there is quite a significant improvement, yeah, in doing like that. Yes. And if not, okay, this closes the chapter. So I think today, yeah, we gave you a preliminary overview, okay? So the lessons learned for today are, okay, data is maybe not all we need in practice, yeah? So if we don't have all the data we need for foundation models, we may need to resort to our domain priors and use them. We learned how to classify machine learning models that incorporate physics priors in 3 categories, yeah? So acting on the inputs, architecture, and loss function. And we had a preliminary look at the first category, physics-guided machine learning. And tomorrow we will continue, you know, with the physics-informed and then other approaches. We will always try to show applications related to the papers. So to let you also understand what exists already, what could be done also in your research to extend one of these approaches, for example. Yeah, so to give you some insights in that. Okay, so if you have, of course, feedbacks or comments, feel free, and we do our best to incorporate them and to discuss them together.
So if you find any other approach that are related to this, yeah, they are really interested to have a look.
Yes, exactly.
Nowadays, there are, I mean, maybe all of the learning pipelines are physics guided, I think. There's
Yes.
a lot of them, because we have a lot of data that comes from video images,
Yes,
but we cannot plug it into it.
exactly.
Yeah, so we can try to get some kinematic references from that. It's kind of
Exactly.
this pre-processing. I think.
Yes. I mean, there is also a lot of approaches nowadays that try to take YouTube videos or videos of robots performing tasks and reconstruct from the video the applied actions. So reconstruct what was actually the action commands to execute that type of video. Yeah, and these are video world models, diffusion models. So there's a lot being done. You can see also these approaches sometimes as physics guided models, because they start from a raw video, maybe, or raw images, and from there reconstruct the forces or the torques. Yeah, exactly. It's not easy to do that because you still need the data to train the model that does that type of operation.
You need to create. Normally, what they do is they are creating some virtual,
Yes,
virtual world where
exactly.
they can collect also this kind of force and then
Yes,
create the image, create the video, and then they train on that, and then they try to verify on real videos.
yes, exactly. But this is an emergent class of approaches. So it's probably, yeah, you're right. It's probably the most emergent one. So the other two classes, physics encoded and informed machine learning approaches, are, let's say, well consolidated. I mean, there is
At least informed.
At least informed. Yeah, the physics informed approaches are well consolidated, let's say. But still applying them is something new. Yeah, so it's something that the community still needs to do. But for these approaches, yeah, physics guided approaches are probably the ones that are emerging right now. So the ones that still need more effort. And that's why also this chapter is the shortest, because there's not so much being done yet. Yes.